Thank you so much for the invitation, Jonathan, and all the organizers. This talk is about reflected resolvent in the Douglas Rachford algorithm, and that would involve talking about the order of the operators and linear rates of convergence, which we already got a lot yesterday from Pontus' talk. And that's based on joint works with Heinz Bauschke and Levin Vandenberg. So the setting of the talk, we will be working on real Hilbert space, so Rn is on board, but we can also allow infinite dimensional Hilbert spaces, little L2. A and B, whenever we mention maximally monotone operator, that's the definition. I assume everyone is familiar with it. And we are interested in maximally monotone operators because they generalize subdifferentials of convex functions, but they can also allow for skew operators, such as the rotator in the plane by pi over 2. So we have three words. The first word is the word of monotone operators. And as I said, that generalizes subdifferentials of convex functions. So their zeros were often corresponding to minimizers of convex function. And then this word has a corresponding word of the resolvents of these operators. These resolvents have very pleasant properties, and it has that we can easily see that the zeros of monotone operators correspond to fixed points of these resolvents. And in fact, this correspondence is what was used in the famous proof of Eckstein-Britzekas to prove that the Douglas Rachford operator is firmly non-expansive by just showing that looking at the multi-parameterization of the graph of the operator constructed by T, it's a graph of a maximally monotone operator, and therefore T is firmly non-expansive. And then there is the third word of the reflected resolvents, which are equivalent to A is maximally monotone, equivalent to the reflected resolvent being non-expansive. And they share the same fixed points as we have seen in Jonathan Eckstein's talk as the resolvents. But from an iterative point of view, they are not very pleasant because non-expansiveness is not enough to guarantee convergence. However, in this talk, we will focus on the third word. So, no wars. Just first word, second word, third word. So throughout the rest of this talk, we will be working, A and B would be maximally monotone operators. And the problem of finding a zero of a sum of two monotone operators is to find an X that satisfies this monotone inclusion. And of course, as we have seen in many talks, that covers many optimization problems. The Douglas Rachford method is a successful technique to solve this problem by iterating the operator TAB. By definition, we can clearly see that it's not symmetric in A and B, so we care about the order here. So the first part of the talk is about the Douglas Rachford algorithm and the order of the operators. And that's a joint work with Heinz Bauschke. So we have convergence result. The first thing to recall is this static result that characterizes the set of zeros of the sum. So we can recover the set of zeros of the sum by just hitting the fixed point set of TAB by JA. So here order matters. And then we have the dynamic results, the sequential results, so sequences. We iterate T. Krasnodębski-Mann iteration would guarantee that we converge weakly to a fixed point, not necessarily the zero that we are looking for, and therefore we need the so-called the shadow sequence. And that sequence will converge weakly to the zero that we are looking for. Now, A plus B is the same as B plus A. So all these results have actually can be flipped in the other order, and we get another operator, TBA. We get another limit, possibly different in the governing sequence and the shadow sequence. And we were motivated by answering the question, how do these two orders talk to each other? How does these two orders communicate? Of course, we don't expect that they are equal. Clearly, they are not equal. You can see a simple example here in R2. Take A and B to be normal con operators of two sets, the ball and the line. And let's see the two iterates of the two orders. So we can start, first of all, by reflecting through the ball, then reflecting through the line, reflect, reflect. Douglas Rachford is reflect, reflect, and then you average with the starting point. So you go halfway through, and that is the order ball first, then line. So that's what we get from that order. That is the first iterate. But you can flip the order. You can actually use it to reflect through the line first, and then reflect through the ball, then connect and go halfway through, you get the other order. So these are the two possible orders. So they are clearly not the same for sure. So we are not looking at proving that they are equal even under some conditions. But we wanted to see, I mean, they solve the same sum problem. The fixed point sets of the two different operators will actually, at the end of the day, characterize the set of zeros which are the same. So we wanted to see exactly what is the deal there. We were so tempted to answer that question. So the first result that we were able to show is those reflected resolvents are actually very nice. They act as isometric projections from the fixed point of one order to the other. So RA would map fixed point TAB to fixed TBA, and that's a bijection, an isometry. And its inverse actually is the other reflector. And the proof of this part is really easy. It will fit in the next slide, very simple. But this is not the entire thing. I mean, we were able actually to be much more specific and talk about how the fixed point sets are mapped concretely, how each point is mapped. I won't dig into details in this. This set SAB here is what's known as the Kuhn-Tucker set. This is also called the extended solution set by Eckstein-Spiter. And in fact, it has something to do with the primal and dual solutions. So we know exactly how the fixed point sets are mapped. The entire proof doesn't fit the scope of the talk in terms of length, but I will only prove the first part that's actually sweet and nice. So we want to prove that RA is an isometric projection that takes one fixed point to the other. These are the definitions of the two orders, and we can easily see that the fixed points of T are the same as the fixed points of the composition of the resolvent, of the reflectors. So we start with an X. That's the fixed points are the same. So we want to prove bijection, so onto, first here. So we start with an X in the fixed point of TAB. It's the same as being a fixed point of the composition of the reflectors. And therefore, you just apply RA to both sides. But when you apply RA to that identity, you can easily see that that would actually correspond to having RA as a fixed point of RA/RB. And that means that it's a fixed point of the other order. So it maps it into fixed TBA, and we can do the same by interchanging the rules. Everything holds. Step 2 is the onto part, very similar in flavor to part 1, so I won't do it. Now we want to prove that RB is the inverse of RA, so we use the fact that, again, RB or AX, because it's a fixed point, is the same as X. So it's actually the inverse. And the isometry part uses that RA is non-expansive. So we start by X minus Y. By definition, because it's a fixed point, this is exactly what X minus Y equals to. But now we use that RB is non-expansive. So we get this inequality. And now we use that RA is non-expansive. We get one more inequality, and we start and end with norm X minus Y. So all inequalities turns to be equalities. So that was the first result, and that is more static. I mean, there's nothing about the sequences, no sequential results. We just learned that fixed point sets can be talking to each other through the reflectors. But we were able to show something sweet about the iterites, the orbits as well. So we were able to show that the reflectors can also do something nice to the orbits. But in this case, that's not true in general. So if we have one operator of U with a closed affine subspace, and we take A to be its normal Kohn operator, something nice happens. If we look at this here, on the left-hand side, this is an orbit of one order, and we can fully map it to the orbits of the other order and vice versa. Okay. And the proof is actually, again, the sketch of the proof is sweet. So the first thing is that because we have an affine subspace, there is something very nice about its reflectors. The reflector is actually an isometry and satisfies this property. So the reflector is actually the inverse of itself. And that's a key property in the proof. Now, we can prove this result by induction. So in this slide, I will only do the base case, and the rest of the result would follow. So we look at this. In the left-hand side, there is this term in red. This identity needs only A and B are maximally monotone. We don't need any assumptions to get this identity. So this is an identity that we can verify just algebraically. And now we have to use the fact that A is an affine relation. U is an affine subspace. Its normal cone is an affine relation. Its resolvent, JA, is an affine operator. So we use this, and the first two terms, we write them like that. The last term will come down as it is. Now, that is the definition of T. So I just plug it here, simplify, and then you will see that what we get is that just 0. So the left-hand side, the red term on the left-hand side is just 0. And now we can just apply our A from the left or the right to get the identities for the case n equals 1, because our A squared is identity. So if you just apply it, you just get the result immediately. Okay. And then the rest of the proof would follow by induction.
So this can directly extend to affine functions. So, or when you do
no, you need affine subspace. And then the other one could be function or any monotone operator. So B could be anything, but you need A to be an affine subspace because the reflected result, the fact that it is the identity, RA squared is the identity, does not hold for affine functions.
Since you need linearity of the J of A, resolvent of A, so it doesn't have to be a affine subspace. It can be more.
This result in red is true whenever, and that's in the paper, is true whenever A is affine relation. So affine functions holds. That's true. But to move to step 3, you need step 1, and that's actually. So exactly. I mean, you for the red identity, and it's in the paper. We prove that this is true whenever you have affine relation, function whatsoever. I mean, even if it's a maximally monotone operator, not necessarily a function, you get this true. But if you want to go back and prove these identities, you actually need to head with the reflector. And this is not true in general. That the reflected resolvent squared, the identity is not always true. This highly relies on the fact that you have an affine subspace. So here's the visualization of the result. So as we see here, that's a convex feasibility case. So the line is affine subspace, the ball. And we start at x naught. These are the orbits. And if we apply the reflector, they are kind of like beautifully reflected. So the orbits are kind of mirrored. And actually, if we replace the affine by subspace by a cone, and this is in the paper, this result does not hold. But sometimes the visualization is not very easy. So let's see where the failure of the results happens. So here I replace the affine subspace with an ellipse, and you can see here that the orbits are no longer, similar in any way. So that result has some impact on other results or other known methods. So this has direct connection to parallel splitting method, because in parallel splitting method, we adapt Douglas Rachford to handle more than 2 operators, 3 or more. So we take the whole thing. Douglas Rachford still here handles 2 operators, but in the product space. And one of the operators will be the normal cone operator of the affine subspace, which we have seen in Rockefeller's talk yesterday called the extended coupling space. We have seen in Alvarez's talk in the morning also. This is a famous, the diagonal subspace shows up in many optimization algorithms. So that's a case where we have a subspace, and the other operator could be anything. The nice thing is that, and the reason I showed some of the results, is that the results are fully algebraic, which means it doesn't use anything about being single value. It will still hold if we replace the resolvent of B by an operator QP, and the reflected resolvent, of course, by 2QB minus identity. And that means that these results will still hold in the non-convex case. So in the non-convex case, we take a selection. If we have the projection in the non-convex would be set valued in this case, and we can take a selection. All these results will still hold. There's a recent work on finite convergence by Bauschka and Dow, and in that paper, they required certain order to prove finite convergence. And they look at finite convergence when solving a convex feasibility problem with a polyhedral set in an affine subspace. The sufficient condition is non-symmetric in U and V, and using this result, we can actually now guarantee finite convergence to the other order. So that was the first part of the talk. And then part 2 of the talk would be on linear convergence of Douglas Rachford method. Seems not connected, but still the key players are the reflected resolvent. And I think you got a feeling of that yesterday from Pontus' talk. So that's a very recent work on archive with Liev and Vandenberg. And recall that this is a problem that we are looking at, and we are interested this time to see when Douglas Rachford gives us linear rates of convergence. Now, I had something different on this slide until yesterday when Pontus gave his talk, and I found that I cannot compete with his excellent summary. So I asked him if he doesn't mind sharing his slides with me, which he kindly did. And then I borrowed the slide and just put it here. So I think it's much nicer than what I had. So mainly, we were so motivated and impressed by the results Pontus presented here. But that was a case that was not in the paper, and we wanted to complement these results by having one operator strongly monotone and the other is Lipschitz. So cases M1, M2, M3 has something in common. Case M1 has strong monotonicity and co-cohesivity on one operator, and case M2 would have strong monotonicity and Lipschitz, which actually results in having co-cohesivity on the operator as well. So we have a co-cohesivity here. In the case M3 have the two properties split. And that's actually nice when we look at it even from a primal-dual point of view, because this means that the sum in the primal is strongly monotone, and the sum in the dual, because co-cohesivity will dualize to strong monotonicity, is strongly monotone. So this is very beautiful. So we were hoping, having near Lipschitzness doesn't guarantee any co-cohesivity, as long as we are not necessarily subdifferentials. If we have a subdifferential or a gradient that is Lipschitz, by the Bellon-Haddad theorem, we know that we have co-cohesivity. But if you have an operator, a skew operator, that is just Lipschitz, then there is no guarantee that you get co-cohesivity, of course. So we were aiming to get something nice as Pontus in terms of these reflected resolvent would have something like being contractive or average, something in that class, non-expansive and some extra, refinement of this non-expansiveness property. And then we tried some examples and tried to see what is the deal. So of course we started by the bad rotator and see what's the deal. So here is an example in R2A, clearly non-expansive, so it's a Lipschitz one. So Lipschitz continuous monotone operator. And B is a super strongly monotone. It's strongly monotone for any mu bigger than 0. And what are the reflected resolvents in this case? So the reflector of A is just as bad as A. It's another skew operator, just Lipschitz, or just non-expansive, no signs of averageness, can't be contractive, nothing. So we start thinking Pontus way again. Maybe when we do the composition, we get something nicer. Maybe the reflector on its own doesn't give us much. He had cases where we have negative averageness. That won't guarantee much, but with the composition and averageness would be nicer. So we looked at the composition, and its negative is not even average. So the composition cannot even be negatively averaged, in which case we could get convergence based on his results. So the composition was really bad, and we were kind of disappointed. We didn't get anything just even close by in flavor. But we still had the feeling, based on his results, that is the reflected resolvent that will create the difference. Again. So it turns out that the property that we're looking for does not belong to the class of non-expansiveness and the refinements in terms of contractions and averageness and all these things. It turns out that the property that could help in this case is actually in the class of monotonicity. So the reflected resolvent of a beta Lipschitz continuous operator satisfies this inequality. And in fact, this lambda is between -1 and 1. If lambda is negative, then, or non-positive, then if it's 0, then this means that the reflected resolvent is monotone. And if it's negative, we are even better, strongly monotone. But if lambda is positive, minus lambda would be negative. And this is a property that was introduced by Rockefeller called hypomonotone operators. And this bound in general is not sharp, but if we are linear and skew, we get a sharp bound. So that was the first ingredient that we needed. And I won't do the proof for this one. But the second ingredient is this proposition here. So the first part, we thought Pontus way, the reflected resolvent. That is the key. Second part, it should do something to the composition. So we start looking at the composition. So we have this abstract result that would apply directly to Douglas Rachford. R is negatively averaged. We have an operator that's non-expansive, satisfy this property. And we define this operator here. Then we claim that we get a contraction. I won't look at this. I mean, these are constants that we can simplify throughout the proof. But I won't care about simplifying them. Let's look at a quick sketch of the proof. So this is the proposition that we want to prove in the footnote here. So the first step is that I look at this operator here. M had these assumptions, and I claim that this is Lipschitz with this constant. So we take S to be this operator, and I examine Sx minus Sy squared. Now, this is just expansion. I didn't do anything. The next step is those first two terms come down as they are. This term comes from this green inequality. I use it, and I get the first inequality. Now, the next term is I just use the fact that m by assumption is also non-expansive, so I get another inequality, and I simplify to this. So we get that it's Lipschitz with the claimed constant, and we can easily see that it's actually strictly less than 2. Now, R is alpha averaged, so we can write it, minus R, sorry. We can write it like that, and n here is a non-expansive operator. So part 2, we use this to rewrite t in terms of m and n. And we look at this. Now, this is less than or equal. We look at this. This is just the triangle inequality applied to to tx and ty, and using this. So that's the triangle inequality. That's the 1/2. The first green term comes from here, and the brown term comes from here. So this is just the triangle inequality. The next inequality, this part comes from the first step, and this part comes from the fact that both m and n are non-expansive. So their composition is non-expansive, and we get an alpha here. Therefore, because this is less than 2 minus alpha, and we get an alpha from here, that would be less than 2, and there is a 1/2 that's strictly less than 1. So we get that this is a contraction with the claimed factor. So this is the key result that guarantees that we have a contraction here. Okay. Now, this applies to Douglas Rachford operator. How? We have a beta Lipschitz continuous operator and mu strongly monotone operator. Don't care about the range that much. We have 2 sequences. The governing would come from iterating the t and will converge strongly with a linear rate r. And of course, the shadow, because JA is the resolvent is non-expansive, would get the same rate immediately. The fixed point set is a singleton, and the set of zeros is also a singleton. The fixed point set is a singleton. If we have a skew operator, if A is a skew operator, we get a sharp rate given by this. And the story is simply, we just make sure that this setting fits the lemma that we just talked about. And therefore, everything will follow, because we will prove that T, in this case, is a contraction, a Banach contraction, so we get strong convergence. Fixed point set is a singleton. And of course, the set of zeros here is a singleton, either through the fixed point sets or also because we have a strongly monotone operator. Okay? So using ingredient 1, we have a Lipschitz continuous operator. We have RA satisfying the hypomonotonicity assumption. And therefore, we can actually check mark this assumption. Pontus proved, and this is what we saw yesterday, that if we have a strongly monotone operator, the reflected resolvent is average. So now the second assumption. And we just blend the ingredients together. So ingredient 2 is just the proposition. And this is what we have. If we convert the two, all we need is to just apply the lemma. R is replaced by RB, M is replaced by RA, and the conclusion immediately follows. The contraction factor is sharp in the case where we have a skew operator. So we can just look at this example. We have here A is beta Lipschitz, B is mu strongly monotone. You take a normal cone operator, which is maximally monotone, and then through a positive multiple of the identity, you get strong monotonicity. So the operator fits exactly the setting that we are looking for. We can calculate, I mean, this is in R2, we can calculate, everything goes down to 2 by 2 matrices. We can calculate the reflectors, take the composition, that is the T. And to find the contraction factor, just take TT transpose and calculate the radius and take the square root, you get the norm of T. So this is exactly the factor that we have in the skew linear case. And this result ties to the primal-dual Douglas Rachford splitting. It works. This is a setting where it works in optimization. So we have a non-zero linear operator and a strongly convex Lipschitz, a function with a Lipschitz continuous gradient. So these are 2 functions. And we look at this monotone inclusion. Here we work in the product space, x times y. A and B here, as we see. If we look at A is a skew operator with a Lipschitz continuous gradient, which is non-zero by assumption. And B is a maximally monotone operator. The reason B is maximally monotone is that the gradient of G is actually more than Lipschitz by the Bellon-Haddad theorem. Yes? Oh, yeah. I have a reminder here, too. Thank you. And the gradient of G is Lipschitz continuous. It's even more than this. It's cohesive by the Walaa theorem. And therefore, when you go to the conjugate, the subdifferential of the conjugate would be another strongly monotone operator. So in the product space, B would be strongly monotone. So we have now in the product space, the bolded A and bolded B are exactly fitting the setting that we're looking at. And this inclusion shows up under appropriate constraint qualification, of course, when we solve primal-dual problems, B and D like that. And this is a setting where, in optimization, where our results are applicable. So that's basically the end of the talk. But since we were talking about Douglas Rachford, this session is about Douglas Rachford. And we had mentioned Douglas Rachford a lot in this workshop. So I think it was a good time to get pictures of our heroes. So the algorithm came from PDEs in the famous paper by Douglas and Rachford. And they were attempting to solve certain kinds of heat equations. And then what's known like right now as Douglas and Rachford was first introduced. I think there was a previous attempt before this paper by Luteau, but the main algorithm as it's known in the current form was introduced by Lyons and Mercier. So they did this ingenious generalization from solving or not even inclusion, identities in 2 and 3 dimensions. We have linear operators that are positive, not even semi-definite, positive definite. In the original setting of Douglas and Rachford, they were positive semi-definite matrices in Rn, single-valued, full domain, and then they have this amazing generalization to operators that are not necessarily single-valued, not necessarily full domain, and possibly infinite dimensional setting. So that was the talk, and thank you.